When discussing artificial intelligence, we often project biological consciousness onto the machine, expecting silicon processors to possess human reasoning. Yet AI is rigid, mathematical logic. Modern AI development prioritizes acting rationally over thinking humanly. The primary objective is to build autonomous agents that identify and execute the specific actions required to achieve the best possible outcome under conditions of uncertainty. This creates a core paradox. These systems do not understand the world. They do not comprehend the text they generate or the images they classify. They execute a surface-level reproduction of intelligent behavior using applied statistics and probabilistic models. Media depictions often anthropomorphize these systems, presenting them as entities with motives and awareness. For business leaders, this creates a strategic blind spot, leading to mismanaged investments based on the perceived intent of the machine. To utilize this technology effectively, we must isolate its mechanical evolution, establish an accurate taxonomy, and identify actual enterprise applications. AI is not a sentient partner, it is a data-driven optimization engine. Managing it through this lens is required for any rigorous integration strategy. The origin of this optimization engine dates back to 1950 and Alan Turing, a mathematician who introduced a concept known as the imitation game. Turing bypassed the philosophical problem of defining thought by proposing a measurable behavioral test. If a machine's output is indistinguishable from a human's, it exhibits intelligence. In 1956, the Dartmouth Workshop officially coined the term artificial intelligence. This gathering launched a period of significant research, backed by the belief that human-level machine reasoning was only a decade away. This timeline tracks computational power and data volume since 1950. Note the drop into the first AI winter between 1974 and 1980. Researchers hit the technical limits of mimicking human reasoning, leading to a collapse in funding. A spike in commercial interest arrived in the 1980s via expert systems, but the timeline drops sharply again shortly after. This second AI winter lasted from 1988 until 2011. These periods of stagnation occurred because early computers lacked the raw processing power and digital data required to function outside a controlled laboratory. The mathematical theories were sound, but the hardware was insufficient. Hardware began to align with theory in 1997 when IBM's Deep Blue defeated the reigning world chess champion. Despite its success, this 1997 system was not learning. It relied on brute force search algorithms and expert-crafted heuristics to evaluate millions of possible moves per second. Early AI was limited by human foresight. The programmer had to anticipate every possible move. Moving past this required a different architectural approach. That early approach is known as symbolic AI. It is an architecture built on rigid, deterministic programming where every decision path is predefined. On the left, symbolic AI operates as a top-down decision tree. To recognize a fraudulent transaction, a human programmer had to hand-code every specific rule and variable that defined fraud. The right side illustrates machine learning. Here, the system ingests a dense stream of raw data, and the algorithm automatically identifies the boundaries that separate different categories of information. Machine learning changes the core logic. Instead of following explicit instructions, the system uses algorithms to identify probabilistic patterns within historical datasets. This approach became viable at an enterprise scale around 2012, fueled by the availability of big data and the use of GPUs. A GPU, or graphics processing unit, is a specialized processor designed to execute thousands of mathematical operations in parallel. The algorithm now identifies the solution directly from the data, which removes the human programmer as the scaling bottleneck. This evolution allows us to classify AI systems across a three-tiered spectrum of capabilities: ANI, AGI, and ASI. Artificial Narrow Intelligence, or ANI, refers to systems designed to execute singular, highly specialized tasks with extreme efficiency. This matrix shows the current landscape. Artificial General Intelligence and Artificial Superintelligence represent hypothetical systems with human-level or superhuman flexibility. As you can see, they remain locked off and grayed out because they are entirely theoretical. Regardless of marketing terminology, every modern enterprise system in operation today is strictly artificial narrow intelligence. Within the discipline of artificial intelligence, a second concentric circle maps out machine learning, the foundational, data-driven subset of the field. At the innermost core is deep learning. This specialized subset utilizes multi-layered artificial neural networks to process massive volumes of unstructured data. Understanding this nested taxonomy allows leaders to procure exact technical solutions, such as a specific deep learning model, rather than buying into vague AI terminology. These conceptual categories translate into real-world business applications across three core functional domains. The first domain is natural language processing, or NLP. This enables machines to comprehend, interpret, and generate human text and speech. The second domain is computer vision, abbreviated as CV. This is the capability to classify and extract meaning from unstructured visual data, such as video and images. These domains form an architectural matrix. Alongside NLP and computer vision, the third pillar is predictive analytics, the use of historical datasets and statistical modeling to forecast future behaviors. In practice, NLP can automate the summarization of legal documents. Computer vision identifies manufacturing defects on a production line. Predictive analytics executes real-time ticket scoring for financial institutions. A horizontal line bisects these pillars to show how businesses integrate them: commodity off-the-shelf APIs on the top and proprietary custom models on the bottom. An API, or Application Programming Interface, is a standardized set of protocols that allows one software application to access the features of another. Off-the-shelf APIs offer basic utility, like routing a standard customer service chatbot. Because these are accessible to any organization, they provide zero competitive advantage. Dominance comes from training proprietary custom models on a company's internal, siloed data. For example, a proprietary high-frequency trading algorithm creates a multi-year economic moat that competitors cannot simply purchase. Competitive advantage is not found in adopting AI generically, but in applying the correct functional domain to proprietary datasets. The current peak of deep learning now exists at a bold new frontier: generative AI and large language models. Early AI systems were designed for classification, such as identifying fraud. Frontier models extend this capability to synthesis, creating novel text, code, and images. These models are automating market research, generating software code, and managing real-time customer interactions. Despite their conversational fluency, the paradox established in Act 1 remains. A large language model is not a replication of human thought. There is no consciousness driving the cursor. These are data-driven reasoning engines. They operate by predicting the next logical element within multidimensional probabilistic maps of vocabulary. To manage these systems effectively, leaders must actively strip away their own anthropomorphic biases. You are not hiring a digital employee. You are deploying an advanced statistical tool. Competitive results will be driven by those who navigate the mathematical reality of these systems, leaving the myths to the headlines.